The binomial theorem. The binomial theorem is used to expand binomials that are raised to any positive integer. For some binomials, we already have patterns memorized. For instance, if we had a plus b squared. This is a pattern you should already be familiar with. Remember, we take the first term a and we square it. Then we multiply 2 times the product of a and b, plus we then take the last term b and square it. Now this is a pattern you should already be familiar with. We also know special patterns for the sum or difference of cubes. We know if we have a plus b cubed or a minus b cubed, there's a special pattern. But what about when you have a binomial raised to a 4th power or 5th power or 6th power? What do you do then? Okay. We can use the binomial expansion theorem to help us expand these. Well, let's take a look at the binomial expansion theorem. To be able to use the binomial expansion theorem, your binomial has to be raised to a positive integer. Okay, so this n has to be some positive integer. Then notice that when we expand the binomial, let's look at this coefficient here. We use what we've learned about combinations to write these coefficients. Okay. Notice that the combination is a combination of whatever the exponent is. That will always be in the n right here, okay, your exponent. And notice how in the first combination we use 0, and then in the second combination we use 1. In the third combination it's 2, so this is increasing. All the way down to the last term will be a combination using the exponent. Okay. Well, let's look at the a term and b term and what we do with those. First, let's look at the a term. Notice with the a term, be this term here. Okay. Notice with the a term, in the first term of our expansion, the a term is raised to our exponent, to n. But then look at the second term. In the second term, that a term is being raised to the n minus 1 power, meaning 1 degree less. For instance, if we had a plus b raised to the 6th power, in this first term we would have been raising a to the 6th power, but in the second term we would raise a to the 5th power, and so on. In the third term, a would be raised to the 4th power, the next term to the 3rd power, the next term to the 2nd power, all the way to the last term we would be raising a to the 0 power. Now let's look at the b term. In the b term, notice we start low. We start at the 0 power, and then we increase by 1 degree each time. B is being raised to the 1st power, then the 2nd power. It would be raised to the 3rd power, 4th power, 5th power, each term raising 1 degree, all the way to the last term would be raised to the power that we have raised the binomial to. Okay. This expansion, the sequence, or series I should say, can be written in summation notation. When we write it in summation notation, let's first look at our upper and lower limit. Our lower limit will always be 0. Our upper limit will be the power that we're raising the binomial to. Okay? So these will match. Now let's take a look at the combination, or the rule. Let's look at the rule. In the rule, we always have this combination in front of our a and b term, okay, where the combination uses the upper limit, the n, the exponent, okay, and then the r. Now r is going to start at our lower limit, which is 0, and for each term that's going to increase 1. Then look at our a term. And the a term, okay, with our a term, what we have is a raised to the n minus r power, which means that we would have our upper limit minus our lower limit. Okay. So n minus r, so first it would be n minus 0, then minus 1, then minus 2, minus 3, so that this exponent is decreasing all the way to 0 for the last term. Take a look at the b term. The b term is raised to the power of r, which is our index. Okay. That index starts at 0 all the way to whatever the upper limit is. That upper limit is the power the binomial is being raised to. Alright. Now, this can be quite tedious if we have to put each one of these combinations into our calculator. Okay. Now again, notice that these combinations, they increase by 1. We've got 0, and then 1, and 2, so on. We have some shortcuts that will help us, or a shortcut that will help us with these, and so that we do not have to punch this into the calculator for each term. It's called Pascal's triangle. Let's take a look at Pascal's triangle. Pascal's triangle is a triangle that lays out the combinations, starting with a group of 0. Okay. If we have 0 items, then the only possibility is that we would take 0 items from that group. So we'll start with that combination. That's the lowest possible combination. And then go on to, if we have 1 item in our group, then there would only be 2 possibilities, either 0 or 1. All the way through, let's just lay out several lines here of possible combinations. Okay, 2 in a group, 3 in the group, 4 in the group. Let's go all the way to 5 in the group. Okay, if we have 5 in the group, then maybe we could take 0 from the group. Okay, remember this is the pattern that our expansion takes. If this was a 5th power, then we would need this combination for that first term. We would need this combination for that second term. Okay, you're looking at this and saying, well, how does this help us? Okay, well, let's look at what these combinations would equal. Okay, what if you had 0 in the group and you wanted to take 0? How many possible groups are there? There would only be 1. What if you had 1 in the group and you wanted to take just 0 from the group? What would that combination equal? That combination would also equal 1. And the second combination, that one combination of 1, it would also equal 1. Okay, you can verify this using your calculator if necessary. The next line of Pascal's triangle, you could use your calculator and lay it out. I'm just going to go ahead and give it to you. The next line of Pascal's triangle would be 1, 2, 1. We begin to see a pattern develop in Pascal's triangle. Notice that the outside line, it's all 1s. Okay. So let's look at one more line so we can more clearly see. Let's go one more line with this pattern. Maybe even a couple more lines here. Now let's take a look at this. How could you develop this triangle without having to use a calculator? Notice that on the outside edges, it's all 1s. Both sides. All 1s. Okay. Then let's look at the terms inside. Notice that this 2 right here, that would be the summation of the 2 numbers above it. 1 plus 1 would give you this 2. Take a look at the next line. Okay. 1 plus 2 gives you 3. 1 plus 2 gives you this 3. So what we see developing is that each term on the inside of the triangle is the sum of the two numbers above it. For instance, this 4, that'd be the sum of the 1 and the 3. This 6 right here, that's the sum of the 3 and the 3 above it. Okay, 3 plus 1 here would give us this 4. Okay, go on to the next line. 1 plus the 4 gives you the 5 there. Let's get some of this out of our way. 4 plus the 6 would give you this 10. 6 plus the 4 would give you this 10. 4 plus the 1 would give you this 5. So let's try to take this one more row ourselves. Notice we have to have a 1 on the outside. We need here a 6, here a 15, in the middle here a 20, and then 10 plus 5 here would be another 15, 5 plus 1 would be a 6 there, and then 1 here. Now again, how can we use this to help us expand? Well, we already know what the answers are to the combinations in the expansion here. Let's say we had a 4th power, a plus b raised to the 4th power. We can take the shortcut using Pascal's triangle. We know that we would need this row right here because we need the combinations of 4. Okay? So these combinations, this one would be a 1. For the second term, it's a 4. For the third term, it would be the 6. Okay? And so on. Okay? All the way down to the last term would be this 1. Okay? All right, let's go to an actual problem to expand. All right, here we go. We have a binomial, 2x plus y squared, and we want to cube it, raise it to the 3rd power. Now this is a pattern that we should already be familiar with. We don't need the binomial expansion theorem, but we're going to use it and then see how that we get the same answer, whether we use the pattern we already know for cubes or whether we use the binomial expansion. Okay? So here we go. Because we are raising to the 3rd power, then we need the row for the 3rd power from Pascal's triangle. So let's put Pascal's triangle here. Okay. So we need this row right here. We know we need the row that has the 3 in it. Okay. We need this row. So our combination for the first one would be equal to 1, and then we need that times A times B plus the next combination would be a 3 times A times B plus the next combination would be a 3 times A times B plus the next combination would be a 1 times A times B. Now A is 2x, so we come back, we put 2x in. Now remember, A starts high. A starts at the upper limit, so this would be raised to the 3rd power. Then this A would be raised to the 2nd power. In this term, A would be raised to the 1st power, all the way down to our last term, A is raised to the 0 power. Let's come back and do the same thing with B. The B term is the y squared term. Remember, in the first term, we start low with the B term. We start at the 0 power, start at our lower limit, and we raise it 1 degree. So in the next term, our B term, which is y squared, would be raised to the 1st power. Then it's y squared raised to the 2nd power. And then in the last term, y squared raised to the 3rd power. Now let's simplify. Okay, so we would have 1 times 2x cubed. 2x cubed would be equal to 8x cubed. And then y squared raised to the 0 power. Remember, anything raised to the 0 power would equal 1. Simplify this, 1 times 8x cubed times 1, then that first term is 8x cubed. Plus, in the next term we have 3 times the 2x squared, so 2x squared would give you 4x squared, times y squared raised to the 1st power. Remember, when you raise a power to a power, you multiply, so y squared to the 1st power would still equal y squared. Simplify this term, so you've got 3 times 4x squared times y squared, or 12x squared y squared. Plus, for the next term, you have 3 times 2x to the first power. Well, 2x to the first power would just be 2x, so 3 times 2x would be 6x, times the y squared squared. Remember, you multiply those exponents, so you end up with y to the 4th power. Plus, in the last term, we have 1 times 2x to the 0 power. Well, remember, 2x to the 0 power, anything to the 0 power equals 1. And then we have that y squared raised to the 3rd power. We multiply the 2 times 3, or end up with y to the 6th power. So you end up with 1 times y to the 6th. Okay, so we have 8x cubed plus 12x squared y squared plus 6x y to the 4th plus y to the 6th. Okay. Now, again, I mentioned that this is a pattern that we really should have already had memorized and not needed to use the binomial theorem. Remember, if you have a plus b cubed, a plus b cubed is always supposed to be equal to cube a plus, the second term would be 3 times a squared times b plus, remember the third term is 3 times a times b, now squared, plus the last term is b cubed. Now let's compare that to what we got when we used the binomial theorem. The binomial theorem, we ended up with 8x cubed. Look at our first term. Our first term was 2x. 2x cubed would give us this 8x cubed. Okay. Then look at our next term that we got with the binomial theorem. We had 12x squared y squared. Okay. We know that if we were just expanding it using our pattern, we should have gotten 3 times a squared b. Well, 3 times 2x squared, 2x squared would have been 4x squared, times the 3 would have been 12x squared, and then times our b would have been y squared, and that's what we ended up with, 12x squared y squared. Okay. Our third term was supposed to be 3 times a times b. 3 times a was 2x, so 3 times the 2x would have been 6x, times the b squared, b was y squared, so y squared squared would be y to the 4th. So we end up with the 6x y to the 4th that we would have gotten had we expanded it using our pattern. Then the last term should have been b cubed. Check it out. The last term, b is y squared, and when you cube y squared cubed would give you the y to the 6th. So it works we can use the binomial theorem to expand this binomial, or we can use the pattern that we memorized. Okay. Now let's look at some that we don't have patterns memorized for. Here we have a plus 3, and we want to raise it to the 5th power. Remember, that would mean a plus 3 times a plus 3 times a plus 3 5 times, or we can use our binomial theorem. With our binomial theorem, we want to take our different combinations, and remember, we can use Pascal's triangle to get these combinations. We just need to go down to the 5th power. So we could develop the Pascal's triangle ourselves. Remember, we start with a 1, and then it's 1, 1 underneath that, and then 1, 2, 1, just adding the terms above it. Always start with 1 on the outside, then add the two numbers above, ending with a 1 again. Then start with 1 again, add the two numbers above, end with a 1. We would want to go all the way to 5. because we're raising to the 5th power. So now we know we're on the row that we need. Alright, so quickly we have found that the coefficients that we need are 1, 5, 10, 10, 5, and 1. Okay, so you can quickly develop Pascal's triangle on your own. Alright, move Pascal's triangle down to the bottom here to give myself a little more room. So these are the coefficients that we need in front of our a and b. So I'm going to start by writing that out first. I need 1 times a times b plus, then I need 5 times a times b plus, I need 10 times a times b plus another 10 times a times b plus 5 times a times b plus 1 times a times b. I'm out of room here. Let's see if I can squish this in a little better. Okay, that fits a little bit better. Now, let's start with the a term, which in this case happens to be a. So we're going to start with the a term. Remember, with the a term, you start at the upper limit. Our upper limit in this case would be 5. Okay, and then we want a to the 4th power, and then a to the 3rd power, and then a to the 2nd power, a to the 1st power, a to the 0 power. Okay, we know that we're done. We're at the last term when we get a all the way down to the 0 power. Now we want to take the b term. With the b term, we want to take b, and we'll start at 0. We're going to start at the lower limit, and when we raise it 1 degree. So then we take b to the 1st power, and then b to the 2nd power. Take the b term, which is 3, and raise it to the 3rd power, and then b raised to the 4th power, all the way till the last term, b should be raised to the exponent that our binomial was raised to. Now let's simplify. Alright, so in our first term, we have 1 times a to the 5th power times 3 to the 0 power. Well, remember, 3 to the 0 power just equals 1, so we end up with 1 times a to the 5th times 1, or just a to the 5th power. Plus, our next term, we have 5 times a to the 4th times 3 to the 1st. 3 to the 1st would be 3, so 3 times the 5 would give us a coefficient of 15 times the a to the 4th power. Let's go to the third term. In our third term, we have 10 times a cubed times 3 squared, so 3 to the 2nd power, or 3 squared, is 9, times the 10 would give us 90 a to the 3rd power. Plus, let's go to our next term. In our next term, we have 10 times the a term squared times the 3 raised to the 3rd power. 3 to the 3rd power is 27, so 10 times the 27, we would have 270 a to the 2nd power. Plus, go to the next term. We have 5 times a to the 1st power times 3 to the 4th power. The 3 to the 4th power would equal 81. Then you want to take 5 times the 81. 5 times 81 would be 405 times the a to the 1st power. All the way to the last term. The last term, you have 1 times a to the 0 power times 3 to the 5th power. Remember, the a to the 0 power equals 1, so we end up with 1 times 3 to the 5th. 3 to the 5th is 243, so we have 1 times 1 times 243. Done. This binomial has been expanded. As you work with this pattern, you should become faster and faster at completing. Alright, let's try another one, see if we can get a little bit faster at this. Alright, with this binomial, we're raising it to the 6th power. So we know in Pascal's triangle we need to go down to where we have the 6th. Okay, so, oops. Alright, so this row of Pascal's triangle will be our coefficients, our combinations. Okay, so why don't you pause it, give it a try, and then come back and see if you were correct. Alright, while it was paused, I've included the work that you should have shown and the final answer that you should have gotten. If you did this expansion correctly, you should have ended up with x to the 6th plus 6x to the 5th y plus 15x to the 4th y squared plus 20x cubed y cubed plus 15x squared y to the 4th plus 6x y to the 5th plus y to the 6th. Okay. If you didn't get that answer, maybe pause the video, compare your work to my work, and see what happened. Alright, so here's another example. Notice this time the binomial is raised to the 4th power, so you're going to need to go all the way down till the 4's appear in Pascal's triangle. Okay. So you're going to need this row. Give it a try. Pause the video, expand this binomial, come back, check your work, check your answer. Alright, if you expanded example 5, you should have ended up with a to the 4th plus 8a cubed b cubed plus 24a squared b to the 6th plus 32a b to the 9th plus 16b to the 12th. If you did not end up with this answer, maybe go back, pause this video, examine the work that I've shown here, find where the discrepancies are. Okay, let's move on to the next example. Alright, the purpose in example 6 is for you to take notice of what happens to the terms when you have the difference of a binomial. So I'd like for you to pause the video, give it a try. Notice it's a 4th power, so you need to go down to the 4th, to where you have 4 in Pascal's triangle. So give it a try. Alright, a couple of things to think about. Whenever it is a difference of a binomial, that second term, the b term, is negative, you're going to first raise it to a 0 power, then a 1st power, 2nd power, 3rd power. Remember, when you're raising a negative to an even power, it ends up being positive. So your first term is positive, your second term ends up being negative, your third term positive, your fourth term negative, your fifth term positive. Okay, so when you have a negative in the middle of your binomial, every other term will be negative. So you should have ended up with x to the 4th minus 20x cubed plus 150x squared minus 500x plus 625. Okay, again, if you didn't get this answer, pause the video, take a look at the work, see if you can find your discrepancies. Alright, for the next couple of slides, I'm just going to pause the video, write just the answer. You should pause the video, give it a try, come back, check your answer, and then if you're having any problems with it, just see me in class. I'm not going to put the work for the next couple of examples. If you've got this and you don't want to practice anymore, don't stop the video. Fast forward to example 8 and make sure you watch example 8. Example 8 is a little bit different. Okay, so pause the video, give this one a try. Alright, if you expanded this binomial correctly, you should have ended up with 8x cubed minus 12x squared y squared plus 6x y to the 4th minus y to the 6th. If you did not end up with this answer, pause the video, check your work, and see what's going on. Alright, let's go to the next one. Okay, pause the video, give this one a try. No, don't forget, write out Pascal's triangle. Give it a try. Okay, if you did this one correctly, you should have 81 x to the 4th plus 108 x cubed y plus 54 x squared y squared plus 12 x y cubed plus y to the 4th. Alright, got one more for you. Pause the video, write out Pascal's triangle, give it a try. Okay, you should have gotten a cubed minus 6a squared b cubed plus 12a squared b to the 6th minus 8a b to the 9th. Maybe you noticed that this binomial was cubed and you maybe use the binomial cubed pattern, hoping that you gave the binomial expansion a try. You need to get familiar with it. Alright, one last example for you, something a little bit different. Alright, example 8. In example 8, what we want to do is find the coefficient of x to the 7th power in the expanded binomial 2 minus 3x to the 10th power. To start this problem, let's take the binomial and write it in the correct summation notation for this binomial. So we want to take the binomial 2 minus 3x to the 10th power and write it in the summation notation. So we would take the sum of r, our lower limit would be 0, all the way to our upper limit. Now remember, our upper limit should be the exponent. Since we're raising this binomial to the 10th power, our upper limit will be 10. Then take the combination. Okay. That combination for this binomial would be 10 combination, and then r is going to change. 0 for the first term, then 1, then 2, then 3, so we just have to leave that as an r. Then we take our first term, a, take the a is a 2 here, so we would take that 2. A has to be raised to the power of n minus r. Well, n is a 10, but r continues to change for every term. Okay. And then we take our b term. B is the negative 3x. And we are going to raise that to the power of r. Okay? And we just have to leave it as an r because r changes for every term. 0, then 1, then 2, 3. Okay, so now we want x to be raised to the 7th power. Notice x is on the b term, so we want that x to the 7th power. That would mean that r has to be a 7. So let's come back, and in our summation notation, where we have r, we're just going to do that term where r is a 7. So we want to do just this one term where r is 7. So we're going to take the combination, put 7 in for the r, take the a term, put 7 in for the r, and then take the b term and put 7 in for the r. Now let's simplify. Now, for the combination, you could use Pascal's triangle if you want to write it out, but you only have this one combination, so just punch it into your calculator. Use your combination button on your calculator. You would find that this combination is equal to 120. Okay, then we want the 2 raised to the 10 minus 7 power. Well, 10 minus 7 would be 3rd power, so we want 2 to the 3rd power. And then the b term, negative 3x, raised to the 7th power. We want the negative 3 raised to the 7th power. That would be, we want the negative 3 raised to the 7th power, and we also want the x raised to the 7th power. Simplify it a little bit further, so we're going to end up with 120 times 2 to the 3rd power would be 8, times negative 3 to the 7th power would be a negative 2,187 times the x to the 7th power. So we've got our x to the 7th power. We just need to finish multiplying and see what the coefficient is. So you want to multiply the 120 times the 8 times the negative 2,187. We can see we're going to end up with a negative term. That final answer, the coefficient would be negative 2,099,520 x to the 7th. So our coefficient right there, that's what they asked us for, the negative 2,099,520. All right, that's the end of this lesson. Hope that this was helpful to you.